Good morning, students. Let us start today's AEC class. Recall the slide which I am showing you right now, where we were discussing about gain margin and phase margin. I was telling about the Nyquist plot and the Nyquist criterion there. Because of the non-idealities of the amplifier, at the high frequency gain keeps reducing, and at the same time the phase response of the amplifier also deteriorates. So in such a case, when the gain keeps reducing, a point will come where at a particular high frequency gain will become 0 decibels, which means as output is falling down at one particular frequency, output will be equal to input. That means amplifier will not be working like an amplifier. Now at the same time, as the phase also is going to be deteriorated, 180-degree phase shift may not remain even at higher frequencies, and even the phase will keep changing. Now you can see in this picture, when the gain is becoming 0 decibels, or when the gain is becoming unity, at that time phase has not become minus 180. I am discussing with respect to a normal amplifier. Now you should not get confused when this particular picture says minus 180 degree, because earlier we were discussing common emitter amplifier, where we were discussing actually 180 degree phase shift coming down to 0. Now here in this example, he is showing some other example, some other amplifier also. In fact, such problems will occur in all types of amplifiers, not just in common emitter amplifier. Every amplifier is prone to such problems. That is because of the non-idealities within the devices. So that way, you can see that when the gain is becoming 0 decibel, phase margin is still there. You can see from the x-axis till the line here, you can see the phase margin. That means there is a margin in the phase shift. Similarly, when the gain keeps on going down further, gain has gone below 0 decibels, means gain has gone below 1 now. Gain is less than 1. After some time, at a particular frequency, the phase is becoming 0. Even though in this picture it is showing minus 180 degree, with reference to common emitter amplifier, the phase shift also is going to become 0 between input and output. Now in such a case, when the phase shift is becoming 0, gain is not 0. Gain is less than 0 dB. That means there is a gain margin here now. So as long as an amplifier is having a gain margin and phase margin, the amplifier will never behave like an oscillator in any frequency. That is the idea here. Because we want amplifier to work like an amplifier only, even if the gain reduces, amplifier should not produce noise on its own. Because basically oscillator means what? Oscillator means it is a noise that is being produced. But somehow we are later on going to discuss oscillators only, where the useful noise we are going to use as a signal or information. So otherwise, amplifier is not supposed to work like an oscillator. Amplifier has to work like an amplifier only. Amplifier should not generate its own noise. That is the idea here. So if any amplifier is not having any gain margin and phase margin at all, then that amplifier will work like an oscillator at a given frequency. That means such an amplifier may not be reliable. Even if we have to use that amplifier for our applications, we should take care that the frequency range will never exceed to that particular frequency where there is no gain margin and phase margin. That is the problem there. Otherwise, let us say there is an amplifier circuit which is not having gain margin and phase margin at all. That means 0 dB and this 0 degree, they are going to match together at the same point. In such a case, at that particular frequency, the amplifier will start oscillating. But you may think, in our application, if there is no such frequency, what is the risk there? But we cannot say, in any application, we cannot say that input signal may have some other spurious noises. Anytime input signal may obtain a larger frequency, because we are working with applications in our real life. In our real life, we cannot say that the frequency range is always limited to every application. For example, when I am talking to right now, I cannot say that the microphone is going to pick up only my voice signal. Of course, the microphone is going to pick up my voice signal also. At the same time, the microphone is going to pick up other natural signals also. Now, in these natural signals, there may be a particular frequency where that particular F may correspond to 0 dB gain and 0 degree phase shift. Then that amplifier has no gain margin, no phase margin. Whenever such particular frequency is input to the amplifier, it will keep on oscillating, and that will be a disturbance. So the idea here is any reliable or faithful amplifier should have larger gain margin, larger phase margin. That means the circuit is reliable and faithful. Let me go to the next slide. I had shown you this slide also with respect to the Nyquist plot. Nyquist says that for any amplifier, this -1 point should be outside the circle. It should not be inside the circle. Now you can see a blue line here. This blue line is basically the combination of the two body plots. That means the gain plot as well as the phase plot. So you can see this blue line. In this blue line, as such, -1 point is outside the blue line, which means this amplifier is stable. Now you can see the notations given here. Between this -1 and this -1 by A, there is a gain difference that is before instability. This -1 point corresponds to instability. That means there is a difference A. So gain margin is 20 log of A in decibels. Similarly, you can see the phase margin here. There is a angle alpha corresponding to this -1 unit circle. You can see corresponding to the -1 unit circle. So, and when this alpha is the angle, phase difference that is before instability, that is phase margin, that is given directly by alpha. So that way, we can actually measure the gain margin and phase margin for a given amplifier. You can see the definition of gain margin here again. Gain margin is 1 over mod of A beta at omega Pc. That omega Pc is the phase crossover frequency. Wherever the phase margin crosses the x-axis or intersects the x-axis. The phase margin is nothing but 180 degree plus angle of A beta at omega Gc. That omega Gc is the gain crossover frequency. That means wherever the gain response intersects the x-axis. Let me show you the definition of GM and PM, which we had done here. You can see here. Gain margin is the negative of the value of mod of A beta in decibels at the frequency at which phi equals 180 degree. At the same time, phase margin, it is the angle of 180 degree minus the magnitude of angle at which the value of A beta is unity. That is what is discussed here in this slide, but in the decibels. Gain margin is expressed in decibels. Okay, this is the last topic with the negative feedback concept. Now let me move on to the positive feedback concept, where we will discuss the oscillators. We have seen the 6 advantages of negative feedback. The only one disadvantage of negative feedback was the gain was being reduced. But we had 6 distinct advantages for that. Now let us see the positive feedback. Till now I have been telling that positive feedback should not be there in our circuit because positive feedback will lead to oscillations. Now, if we give positive feedback to the amplifier itself, if it produces oscillations, that oscillation is also going to be useful for us. How is it going to be useful? Let us see from now on. Now you can see this particular picture. There is a circle here at the left side, and if the circle is cut into so many small segments, and let us say the circle's periphery itself is joined with the same segments. You can see the yellow lines inside and the green lines inside. And let us say the circle is moving. It is like a bicycle's spoke wheel, let us say. And let us say these are all spokes to a bicycle's wheel. Now, let us say wherever this spoke is touching this particular circle, when the circle is moving, that particular dimension or y-axis intercept, let us take it and let us arrange it together. You can see it here. The very first red line is touching here. Let it be here. Then the second line is touching here. Let it be here. Third line is touching here. Let it be here. Fourth line is touching here. Let it be here. Let me annotate. Let me show it to you clearly. Let me change the color. And now you can see this is connected here. 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 This way it goes on. See, this way it goes on. Let me connect all of them. Let me reduce the pen size. See, I am connecting all the intercepts and then that final upper intercept, I am connecting it this way. So when I have connected all these, you can see it has become a sine wave. Let me stop annotating. Now you can see that all these lines, if they are joined till the top, it has become a sine wave. Now similarly, there are other intercepts at the other side. When we join them, all of them, it is going to become a sine wave. That means the movement of the wheel, if that wheel's micro dimensions are plotted in the x-axis, now that is going to result in a sine wave. This is a beautiful concept. Now what is this x-axis? The x-axis is basically t. X-axis is basically time, which means the wheel is moving. When the wheel is moving, the movement of movement of wheel is with respect to time. So with respect to time, when we plot the intercepts of the movement itself or the dimension of the wheel itself, you can see as if the wheel is moving, we are taking a small intercept and then we are connecting it, and that is going to become a positive cycle's sine wave form. Similarly, the wheel has got the lower side. Now the lower side, taking the center of the wheel as the reference, we have to plot the lower side of the wheel to the other side. Now resultant is a sine wave. So what do you understand by this? What do you understand? Any cyclic movement, if it is plotted with respect to time, it is going to result in sine wave. Now you may think, as circle is there, it has got two semicircles, we should actually get semicircles like that, isn't it? You may think that way. You may think that because this cycle is made up of half semicircle and another half semicircle, when we plot, we are supposed to get, let me write a neat line. What you may think is, when we make the wheel to move and when we plot, we should get distinctly a half circle and a half circle. I am not writing it very neatly because I am using the mouse only to write. Now let me stop this. You will have to visualize this. You may think that we should exactly get half circle at the top, half circle at the bottom. But that is not happening so. Why is it not happening so? Because it is a minute movement which we are plotting. When we make a minute movement, the circle's movement itself is going to result in a sine wave. So, even though we think that we have understood the circle, we have not understood the circle so clearly. Even when Archimedes kept on thinking about circle and sphere, even till then people did not understand the mathematical properties of the circle or the sphere until Archimedes specifically formulated it, right? So even though we think that circle is a very simple geometrical shape, have we really understood this circle? Why circle has got one continuous number as pi? For the circumference, we have the formula 2 into pi into r, where pi is 22 divided by 7. That pi is a never-ending number, right? 3.141, it goes on. It is never going to end. It is an infinite number. Why Archimedes specifically used pi only? Why not an approximate number? Can anybody tell me? For the area of the circle, the formula is pi r squared, and for the circumference of the circle, the formula is 2 pi r. Why Archimedes exactly used this pi, which is 22 by 7, which is basically an irrational number, which is a never-ending infinite number? Why he did not use any discrete number or a distinct number? Here it is already written, right? 3.14159, it goes on, dot, dot, dot. It goes on like this. Why he exactly used that pi? Can anybody tell me? Can anybody tell me? I had given you one more small work. I had asked you to tell me why that square root of minus 1 is being used. No one has told me till now. Okay, sine is giving the answer because the sine wave is never ending, like it is not definite. That is fine. Yeah, sine wave is never ending because the circle is moving, right? As long as the circle keeps moving, it will keep on producing sine wave. That's all. Please understand that sine wave is the resultant of the movement of the circle itself. If the circle does not move, sine wave will not happen. That is fine. So we have understood that when we have a movement of a circle, gradually it will result in a sine wave. That is why in all our signal analysis, sinusoidal function is the basic function. Everywhere we are using sine theta as the basic function. Later on, using sine theta, we define all other things. And that is how sine function is related to trigonometry also, calculus also. The sine wave becomes the basic function because of the cyclic movement. Okay. So that is one particular answer for the nature's functionality. In nature, you can see all the planets are spherical in nature, right? Earth is spherical, Venus is spherical, Mars is spherical, because they are all moving, they are all rotating as well as revolving. When they are rotating as well as revolving, gradually they will have a spherical shape. Whenever they have a spherical shape, normally any waveform that is produced due to the movement of these planetary bodies, that will be in the shape of sine wave. That is the mystery of nature which is revealed now. Okay, even a water droplet as it is spherical. Only when it is falling down, it may assume some other shape of droplet. Otherwise, if you take a water droplet just like that, it will be spherical ideally. If it is on the surface, it may be elliptical or parabolic or whatever. But ideally, it is spherical. Every particle is spherical. Even an electron is spherical, right? All atoms, molecules, they are all shown or visualized as if they are all spheres. Because of gravity. Because of the working of the gravitational pull and push throughout nature. In general, all these are spherical. Only in our mathematical analysis, we have rectangles, squares, and cubes. They are actually artificial. In the sense, in nature, you will not see perfect squares, perfect rectangles, perfect cubes. We make them. Let us say we have a sphere, we cut it into a cube that way. Otherwise, nature is basically having circular and spherical shapes. That is because of the cyclic movements. And that is why we have sine wave. That is one of the fundamentals of science now. Now your answer is somewhat all right. But my question is not fully answered. In the sense, let us say sine wave is never ending. That is because of the movement of the circle itself, right? It is movement of the cycle. But my point is, for representing the circle itself, even if the circle is steady, let us say circle is not moving, even if the circle is steady, then also we use 2 pi r and pi r square. My question was, why did we use pi there, or why Archimedes used pi there? Can there be any other answer? Any other answer? Okay, let me tell the answer. The answer is, circle is a continuous, minute movement of the shape. Now let me annotate. Let us say I write a rectangle. I write a rectangle. Imagine this is a rectangle only. Because I am writing through mouse, it is not a perfect shape. When it is a rectangle, we know that the line is going up and it is remaining horizontal, it is coming down, it is remaining horizontal. That means it is discrete. Discrete in the sense it is distinct. In the sense the line remains 90 degree, then abruptly takes a 90-degree turn, becomes horizontal until some point, again comes down, again goes left. So a rectangle or a square or a cube, they are of discrete shapes. Their dimensions are discretely or distinctly defined. What about a circle? Circle shape is continuously changing. You can see at any point its shape is continuously changing. We cannot say that at a particular point the circle will have a discrete or distinct dimension, because in the next moment itself it is going to change. It is not the case with rectangle or square or cube or any such other shapes which are having straight lines. All the shapes which are having straight lines as their edges can be distinctly and discretely defined using a discrete number, using a distinct number. Now it is not the case with circle. Circle cannot be represented with a discrete or a distinct number because its dimension is continuously changing. That is the reason Archimedes used a continuously changing number. That means the number is not a discrete number, it is a continuous number. For the same reason, in trigonometry, in calculus, you are going to use another term called E. You are going to use the term E. E power x and e power minus you are going to use continuously. Why are you using E, and why are we later on saying it is exponential decay, exponential charging for our RC circuits? For the same reason, because the charging curve and the discharging curve is also going to follow this continuous movement. All the charging and discharging of R and C is not going to happen discretely or distinctly. They are going to happen continuously. When they are happening continuously, any continuously changing waveform should be represented either by means of the number E or by means of the sinusoidal functionalities. So you can see that they are all related that way. Even pi and E are related that way. Only thing is the constants will change there. In the sense, you will have AX, BX, CX, or A into e power x, B into e power x, C into e power minus x, like that it goes on. Similarly, when you use sine functions, you will have A sine theta, B cos theta. The constants are going to change there, that's all. Otherwise, pi and E both are continuous numbers. And E was named that way because of honoring to the Euler, honoring to the great mathematician Euler. That is why it is named as E. So that way, numbers and curves are strangely related that way. That is when analog is more challenging than digital. Even in electronics domain, analog designs are more challenging than digital designs. The reason is digital designs are discretely defined, either a 0 or 1, and all the digital circuits are discretely defined, only switching on, switching off. Whereas analog designs are continuous. Analog signals are continuous, representing a continuous waveform or analyzing a circuit which is continuously producing such waveforms. That is difficult, that requires lot of basic analysis or fundamental analysis. And for my other question, nobody has still given the answer. Why we have to use I as square root of -1? I'll keep waiting. I'll keep waiting until somebody gives me some answer. Now I hope you have understood why I have put this picture here with the circle and the waveform. Let me proceed further. You can see this beautiful animation now. I honestly admit I did not produce this animation. I simply copied from Google Eshwar. Google Eshwar gave me anything and everything freely, right, most of the time. So in Google, somebody has put this beautiful animation about oscillators, and I have put that animation here. You just observe for a few minutes. I will remain silent. Okay, there are 33 students watching this animation now. I hope so. All of you are watching. Now, if you are watching, you put your observation in the chat box and tell me what do you understand by this. I did not get any answer. Nobody is taking an initiative to respond to a teacher's query. What, students? In general, we don't like the teaching learning process to be one-sided. Okay, people are putting answers at least. Rohit has put the answer as cyclic production of waves. And Lokesh has put the answer, all three waves have a phase difference of 90 with respect to each other. Yeah, this is a good observation. You can see it again here. You can see, depending upon the dimension of the circle now, or depending upon the radius of the circle, it is the radius of the circle which is defining the maximum amplitude of the sine wave. You can see this. The green circle has a smaller radius, red has a mid-level radius, and blue circle has a larger radius. Now when they have all these three radius, gradually the blue circle is producing a sine wave of the largest amplitude, and the green circle is having the least amplitude. The red one is in between. That is one thing. Second thing is, there was an observation that about the phase shift. Now that is also right. Let me admit a student. Yeah. You can see that depending upon at which particular place we start our 0. 0 means time instant at which we start this oscillator. Imagine that way. Or the cyclic movement. Depending upon that, we can have multiple waveforms with different phase shifts. You can see that green and red wave is having a 90-degree phase shift. Whereas, what about green and blue wave? You know that green and red is having a 90-degree phase shift. What about green and blue wave? Green and blue wave is having a phase shift of 180 degree. You can observe that. Green and blue wave is going to have a phase shift of 180 degree, whereas green and red is going to have a phase shift of 90 degree. What about blue and red? Blue and red is going to have a phase shift of minus 90 degree. So it depends on at which particular time instant we initiate the oscillators. Depending upon that, we can have phase shifted waveforms also. So this is a beautiful animation which indicates all the basics that way. Okay, in this way, I have just shown you a demonstration of how basically oscillators are working. Oscillator means it is basically a cyclic movement. Now in electronics, what is going to happen? In electronics, the cyclic movement is going to happen in a way we feed the output back to input and we will introduce a positive feedback. When we introduce a positive feedback, output comes back to input and it keeps on producing such cycles. That is the idea. So first remember, we are discussing oscillator as a primordial element. Later on we move on to electronic oscillators. Right now whatever I have discussed is basically an oscillator which is natural, which means any cyclic movement in nature, if we plot it in a time scale, then we are going to get a sine wave. Now we are plotting it in a time scale, please remember that. To represent the output of the oscillator, we are plotting it in with respect to time scale. Okay, and as and when this oscillation is coming out, we are going to use it for our purposes. That way, sound is also an oscillation. When you say 20 Hertz to 20 kilohertz is the audible frequency range of sound, what does it mean? It means sound is basically having a frequency. When sound is basically having a frequency, what does it mean? It is an oscillation. Please understand, when you play guitar or veena or sitar or any such stringed instrument, when you pull that string and release it, what actually is happening? The string is moving to and fro. String may be moving up and down or left and right or to and fro. When the string is moving to and fro, that movement is going to create a vibration in the air medium, and that vibration is going to become a sound there. So how the sound was produced? By the movement of the string to and fro. Now that movement itself is going to cause a sound. That is again a cycle. Cycle in the sense, there is a to movement, there is a fro movement, there is a bottom movement, there is a top movement, or there is a left movement, there is a right movement. Now we cannot say that is always a positive cycle or negative cycle. We can say it is left cycle or right cycle, top cycle, bottom cycle. We can say to cycle, fro cycle. Because it is the reference which we take. For example, if we take this x-axis as 0 reference, then we say upper one is positive cycle, lower one is negative cycle. But when you play a string in the guitar or sitar or veena, we cannot say it is positive cycle or negative cycle. It is simply to and fro movement. Right now when I am talking to you, you are listening, what actually is happening in my throat? It is the vocal cord which is moving up and down. When the vocal cord is moving up and down, with reference to the x-axis, I should say, it is upside and downside. We cannot always say it is positive side or negative side. For our mathematical references, when we represented these signals as waveforms in the graph sheets with the 4 quadrants, then we mention it as positive cycle or negative cycle. Otherwise, strictly speaking, in the signals that occur in nature, there is nothing called positive cycle and negative cycle. We define it that way for our reference. You will have to understand these basics also. So that is how we have all these signals generated in nature. So sound is also an oscillation because sound is a movement of a particular object. Now when somebody plays a flute, what happens inside the flute? The air column inside the flute is vibrating up and down within the bamboo body, right? Flute is made up of bamboo. Now that bamboo body is going to vibrate based on the movement of the air which is within. And based on that, when the bamboo body itself is vibrating, that bamboo body's vibration is resulting in a sound there. There is nothing called positive cycle and negative cycle. It is only to and fro movement or up and down movement or left and right movement. It can be a omnidirectional movement. In the case of a flute, as it is a resonant instrument, it is an omnidirectional movement. Unlike in the guitar or the sitar or the veena, in the case of a stringed instruments, it is only two directions. Whereas in the case of resonant instrument, it is all directions. For example, when you play tabla or mridanga or ghata, what is going to happen? It is only up and down movement. Either the plastic diaphragm or the leather diaphragm which is covering that tabla or mridangam or ghatam. In case of ghatam, it is the mud itself, mud pot. So that particular object is going to move up and down. In case of mridanga, it is left and right. In case of tabla, it is up and down. So that way, in some instruments, it is like a directional movement. But in the case of resonant instruments like flute or in instruments like nadaswara, sometimes people call it as nagaswara also, it is basically nadaswaram. In such resonant musical instruments, the signal is produced by means of omnidirectional vibration. So, right now I showed you the picture of normal oscillator or natural oscillator. Natural oscillations are present everywhere, anywhere. Wherever sound is produced in nature, it is basically a movement of a particular object. Maybe living, maybe non-living, whatever. Now that itself, when it is audible, we call it as audible sound. Audible sound is an audible frequency, 20 Hz to 20,000 Hz. A frequency is always an oscillation. Remember that. Frequency is always an oscillation in the sense AC is always an oscillation. DC is discrete or distinct or defined. DC is defined for its value. AC is not defined exactly for its value because it is instantaneously changing. You can keep seeing here all these three waveforms, their amplitudes are instantaneously changing. We can define their amplitude only at a particular time instant. We can define their maximum amplitude that way. Otherwise, at any particular instant, we can define all other times the amplitudes are continuously changing. So, now let us start discussing electronic oscillator. I will go to the next slide. Let us start discussing electronic oscillator because in electronic oscillators, we have to produce some sounds which will be useful to us. For example, a siren sound is an AC sound, but that has to be produced by an ambulance vehicle that is required. At many places in the industries, whenever they have morning 9 o'clock starting time, there is a big siren going out of the factory or the industry. It is an alert that all the people have to come into the factory now and the work should be started. Now that is again a big sound which is alerting people. That is an oscillation sound. And let us say in the broadcast channels, maybe in the FM radio channels or in the television channels, before the actual broadcasting of the audio or video starts, you can see even in the television channel, you can see a color pattern along with the sound. That color pattern indicates that color transmission is happening properly, and that sound indicates that sound transmission is also happening properly. It is an alert to the viewers that shortly the actual broadcasting of the channel is going to happen. It may be news, it may be movie, it may be any other program. So in such cases, that particular oscillation is required, right? For producing that particular alert sound, oscillation is required. Even in your mobile phone, when you set an alarm clock, let us say you are not setting a music as an alarm. In the olden days, alarm also used to be a particular sound, beeping sound. Many times for alert, beeps are used. All these beeps are basically what? Any beep is basically an alert sound. For example, even in medical equipments, all the medical equipments have this beeping alert signal. That is basically an oscillator that produces that beep, and the oscillator is gradually switched on or switched off for getting a continuous beep or a non-continuous beep or a discrete beep. But that beep sound itself is AC. That can be controlled later on by switching for its transmission. That way, digital and analog can be clubbed together. For example, oscillator is completely analog. Now, the oscillator can be connected to a particular timing circuit using digital circuits, and the oscillator's output can come out to the switch, which is a digital circuit. Out of the switch, now the signal will come as we require it, like a shorter beep or a longer beep, beep with time duration in between, beep with gaps in between. Maybe gaps also can be programmed as larger gaps or smaller gaps. All that is possible. That is called as hybrid circuit then. Means analog and digital together, that is a hybrid circuit. So what is the theory of sinusoidal oscillation? Let us see that now. With respect to the input, the gain of the amplifier is minus A. This we already know. Due to the phase shift of 180 degree, that also we know. Because of the phase shift of 180 degree only, gain is becoming minus A. If the feedback circuit also produces an additional phase shift of 180 degree, then B is positive. And the overall gain equation, we are going to see that later on. First understand this. Because of the phase shift of 180 degree, gain is negative. Now, if the feedback circuit also produces an additional phase shift of 180 degree, this we did not discuss till now. Till now we discussed that phase shift is not produced by the feedback circuit. We have been discussing only negative feedback. Now, let us say the feedback circuit also produces a phase shift of 180 degree. Then the feedback signal which is going to the input is going to be in phase with the input signal. Then that B or beta is positive. In Malvina book, he used the symbol B, and in the Boyle stud book, he used the symbol beta. Here in my slide, I am using the symbol capital B itself, just to distinguish that it is not the beta of the device. I have been telling you this again and again. Here I am using the symbol B itself directly. You can take it as beta also. Now this B is positive, and the overall gain equation is what? The overall gain equation is AF equals A by 1 minus A beta now. Earlier we had A by 1 plus A beta. Now because of the feedback circuit which is producing a phase shift of 180 degree, now this is A by 1 minus A beta. Now look at this 1 minus A beta. If at all this A beta becomes 1, we had seen in the Nyquist criterion that if A beta becomes 1, amplifier is going to become completely unstable and it is going to become oscillator. Now, that was a disadvantage there when we discussed Nyquist criterion. Now, we have made it as an advantage. Whatever was the disadvantage earlier, we want to make it as an advantage now. For example, now the advantage is when there is 1 minus A beta, if at all we make our circuit in such a way that A beta is equal to 1, or the product of the amplifier gain and the feedback circuits percentage, if it is going to be unity, then AF is going to become A by 1 minus 1, that is going to become A by 0, that is infinity. That means now the circuit will act like an oscillator and it is going to produce a cyclical waveform. Output will be always fed back to input and we will have a continuous output waveform. and that will be a sine wave form only normally. In case of all analog oscillators, it is going to be a sine wave only. Whereas later on we will be discussing digital oscillators also. Not fully in our course, but we will have digital oscillators also, which will produce only square waves. Whereas analog oscillators, most of them are producing sine waves. Now, we can convert an amplifier into an oscillator by making the factor A beta equals 1. You can see that here. Amplifier is going to give a voltage gain, and this is the feedback circuit. The feedback circuit's output is fed back to input. Now, output is taken back. If A beta is 1, now the circuit will become oscillator, and you can see that the circuit does not have any external input. We need not give the input to this at all. As soon as we switch it on, it will start working. But without getting input, how do we get the very first input? For that question, we will see the answer later on, maybe in the next class, not in today's class. So this way, you can see that A beta equals 1, amplifier is going to become oscillator, and this circuit is going to have a positive feedback, means the feedback circuit is also going to generate 180 degree phase shift. So, if the amplifier is provided with positive feedback, and if the feedback signal is in correct phase with the previous input, then there will be an output signal without any external input signal. That is the basis on which we construct oscillators. If the amplifier is provided with positive feedback, which means the feedback circuit should produce additional 180 degree phase shift. If at all we use a common emitter amplifier at the top, common emitter amplifier is going to produce 180 degree phase shift. We should have one more feedback circuit which will produce additional 180 degree phase shift. As usual, we are always using common emitter only because of its better performances. That is why we keep on giving the example that amplifier's phase shift is 180 degree, even the feedback circuit also has to produce a phase shift of 180 degree now. So if the feedback signal is in correct phase with the previous input, then there will be an output signal without any